Start recording.
Let's go.
Okay, so if you guys can see this, get the chat open as well. So last time we got through everything in computer architecture, which includes how we end up exposing computer functionality to a programmer. And the interface that we discussed was basically assembly programming, which kind of sucks for a lot of applications, primarily because it's cumbersome to work with. And today I think I'm going to start with why there was historically a need for something on top of assembly or something more advanced than assembly, and then get into what that new language looks like. Today's going to be kind of long, so if we end up going over, I can definitely push this to next session, just so split this section in two. Let's see. Okay, so assembly is a little weird in that we have fixed width instructions. So we have an opcode that takes some number of bits in memory to store in an instruction. And then it's operands, which also take some number of bits to store. When you have an opcode that's already part of the instruction, then you're taking away from the total number of bits that you've left to represent data, which means your instructions that involve accessing and loading and storing memory registers, or memory and registers, they can't take up the entire bit space that your machine offers. So if your instruction is 16 bits and your opcode is 4, then you only have 12 bits to represent either an address or data, which means that it's possible that your memory addresses, when you're trying to pass them to assembly-based instructions, don't actually fit in the instruction. So say you have an instruction at the beginning of program memory, and you'd like to jump or branch into something at the very end of program memory. You can't necessarily do that if you can't represent the address of the thing you'd like to jump to. So you have to do so indirectly. So you either have to keep that address in a register and do that branch based on some register value, or in the case where that's not possible, so like you filled up like registers, then you have to do like an intermediate step. So you have to create a jump point that's in between where you start and where you eventually want to end. Jump there, and then jump to the final location. So this kind of like address math gets to be difficult to work with, especially when your program gets really large, because you as the programmer need to know when you're going to need like additional space to represent an address during a jump. There are other reasons why assembly is just cumbersome to work with for large programs. Mainly, you kind of have to have the entire picture of what your program is going to be before you start implementing it. In part because of this address stuff, but also in part because like it just gets really long and you need to know where to be able to find specific subroutines, how you're organizing your data, how much stack space you end up having. And this is all like stuff that's difficult to measure after you've already implemented the system, but is somewhat predictable if you're trying to plan the whole thing out. But the gist of it is assembly projects get big fast if your application is complex. And in terms of labor hours, that ends up expanding the expense of developing in assembly. Another issue with it is it's not really portable. So like I mentioned earlier, assembly is kind of tied innately to the machine that the instruction set is exposed on. That's because each computer may have different sets of instructions that they provide. So there is some portability. For instance, if your machines share the same instruction set architecture, but you can't really rely on that, especially nowadays with all of the consumer grade computers being split between a couple different instruction sets. So like hex86 versus, there are some like ARM based computers nowadays that are suitable for personal computers, and a couple others. But assembly isn't portable. So there arose a need to represent program descriptions that could be moved between machines easily. And so the solution to all of these problems really was to develop what's called a high-level language. And that's just something that is more abstract than C, or so more abstract than assembly. And the language we're going to talk about is C, which was originally developed for developing operating systems. So it's definitely not the first systems programming language or high-level language. You may have heard of like BASIC before, COBOL. There was a B language which predated C, hence the name. But C does remain the most popular, especially in embedded systems. So that's mainly why we're going to go over it, is because it's very easy to program microcontrollers using C. So there are many capabilities in C. That's why today is going to be pretty long. So the main focus of it is that C provides structure. So if assembly is kind of a Wild West, C looks to tame a bit of that behavior by creating a more formal syntax than assembly. It also provides data scoping. So in assembly, you can access any address from anywhere, but with C, based on the language convention, you can access or intentionally hide certain variables. It also provides data typing. So in assembly, memory is just memory, and you have to rely on the instruction itself. So the opcode knows kind of which data it can operate on. So for instance, there are floating point instructions that are dedicated. There are instructions that kind of assume that you're working with unsigned integers, and so on. And in C, that whole paradigm changes because the variable itself now holds the type of information that it contains. So when you type a variable, you know that this set of memory addresses should contain this type of data. So all these kind of combine to provide the kind of flexibility and power that C offers on top of assembly. So this will just be a really long laundry list of all the functionality that C exposes. I'm hoping that most of this makes it in because I'm going to be using C to explain what's going on in microcontrollers when we get to the examples. So it is more important today to understand what I'm talking about than probably everything prior. So I just briefly mentioned data types. So again, that's like, are you trying to represent a 4-byte integer? Are you trying to represent a float, which should be an IEEE 754 representation? And so on. So the kind of data you're trying to represent is its data type. And the container that we store that in is called a variable. So a variable describes both the data type and its place in memory. I'm going to mute you, Diego, if that's okay. Yes, so variables store a value in memory somewhere, but also have the data type associated with the variable. For future reference, that's called statically typing. So when you have to already associate a memory segment with a data type at build time. There are some languages that can do dynamic typing, so you don't know the data type ahead of time, but you do know the variable stores something. That's not C. C is statically typed only. There are a couple data types that are supported out of the box in C, and these are the data types that can't really be changed. So they're called the primitive types. So there's a long list of them. Stuff that's going to be really important. Int stores an integer type. By default, this is a signed integer. And the length, so the number of bits used to represent it, is actually machine dependent. So unfortunately, all of the integral types are machine dependent in terms of size. There is a way around this that I'll briefly mention coming up. This type char represents like a printable English character. It is almost always 8 bits in size, and you can use a character to represent ASCII text by default. So I think I mentioned last time, it's a way of encoding characters as some binary value. So like a decimal 65, if you convert that to binary, represents a capital A, and so on. And so C knows how to manipulate data that's typed as character as kind of things that are printable or human interpretable. Void is a special type that represents that there isn't data storable at this in this variable. So usually you don't use void outright. Usually you can refer to something that is void, and I'll get into that later. You can also, of course, represent floats as IEEE 754 format. So a float in C is 32 bits. So I know I talked about you can have different representations of floats or different bit widths. So C's float is 32-bit. A double is another kind of floating point variable. It just has 2 times the precision. So a double precision float, or 64 bits. There are also these modifiers, so like short and long, to describe, like they modify the default size of the variable you're trying to point to. So there's no such thing as a short character because you can't really get smaller than 8 bits, but there is a short int and a long int and a long double. A short double would basically just be a float, which is already represented as a different type. So that's why it doesn't exist. But I mentioned all the integral types don't really have a fixed or known bit size, or rather it's flexible between machines. If you do need to describe an integer type that is a known size, there is an extension to C. So there's a library that you could use that provides these kind of like pre-sized types, which are guaranteed to be the bit width as long as your machine is capable of representing that bit width. So there are some machines that can't natively support or represent 64-bit integers, for instance, or even some machines that can't support 8-bit integers. Those are exceedingly rare, so I wouldn't worry about it. For now, you can just assume that these integral types, so these uint8, uint64, and so on, can represent their specific widths on each machine. So I mentioned integers, so ints are signed by default. You can also add an unsigned modifier before you call out int in order to designate that it's an unsigned integer. And that's what these u's represent for these uint types. And likewise, the int types are signed. So these are all the primitive types that you can represent. So in sum, what you're probably going to be working with most in embedded systems where the bit sizes are very important are void, character, the integral types represented using their known width representations, and then float and double. So there are, when you are calling out that a variable exists, there's a specific syntax for doing so. And remember, syntax is like a grammar or a set of rules for how we express a phrase. So in C, those phrases are still instruction statements, but they're not representing machine instructions directly. They're instead representing C's notion of what constitutes a program statement. And that's either declaring that something exists or assigning it or operating on it. So if we're only declaring that a variable exists, or if we're only stating that a variable exists, we're just declaring the variable. So it hasn't been given a position in memory yet. We just know that there is a variable with this name and this type somewhere. But when we associate a memory space with that variable, it's called definition. So we define the variable. And then when we give the variable its first value, we're initializing it. And that's just terminology that's specific to C and most high-level languages nowadays. After we declare a variable, we can't actually redefine it. So if you're associating a variable name with a type, that variable name is basically locked in. There are certain cases where you can reuse names, and I'll get into that later. But for the most part, safe practice is always using different names for your variables. So the actual format, the syntax for doing a variable declaration looks something like there's a set of modifiers that's possible. So like signed or unsigned, and there are also other modifiers that I'll talk about. You then state the data type that you're trying to represent. So most likely it's going to be one of these. However, there are some advanced types, again, that I'll talk about later. And then you can have the variable name or a list of variable names that are comma separated. And that's if you have a list of variable names, they all share the same data type. They're different variables, so they'll be allocated in different memory addresses, but they're the same data type. And that's just for brevity, so making sure your code length doesn't get too long. So what actually constitutes a variable name is basically any alphanumeric character or underscores that doesn't start with a number. So some examples of this are, I'm declaring that a character called letter exists, and we'll note the underscores. I'm declaring a list of uint32s, so unsigned integers with bit width 32 bits. Notice the numbers, and it's in the list format. You can have spaces in between these names, doesn't really matter. A list of floats, so XYZ for representing some coordinate, or the unsigned modifier using the short representation, so a short integer with a really janky name. So there are a bunch of ways that you can name data, but point being, these are all just identifiers for some variable that has a data type that's associated with some kind of memory. So once you have a way of representing information in the form of a variable, we now need a set of operators that can modify those variables somehow. So in C, there are a lot of operators. I won't go through all of them, but there are the arithmetic operators that we've come to know. So addition, subtraction, multiplication, and division. Assignment is C specific now, or rather high-level language specific. Assignment means you are taking the value stored in the right-hand side variable or statement and storing it in the left-hand side variable or statement. And really, this is the equivalent of having a register and copying some value into the register, or having a memory address and copying some value into the memory address. So assignment is pretty straightforward. If there are questions about it later, I can talk about it more. There's a new arithmetic operator called modulus, and all it is the remainder after you do a division. So if you have like two integers, if you do a division with integers, by default, the operation should be the floor of that value. And in math, the floor is just the whole number part only of that result. The modulus operator just gets you the non-whole number part as represented by a remainder. So if you divide like 5 by 2. There's going to be some remainder, and that's what modulus gives you. There are also new operators called increment and decrement, and all that does is increase or decrease the value of a variable by 1. And there's, as C is parsing complete program statements, you could have like this operation A++ as part of a bigger statement. So where you put the increment or decrement operator does matter. If you put it before the variable name, it's called pre-incrementing, and that just means that increment happens before the full statement is evaluated. So if this is part of a bigger combination of operations, that ++ happens first. Likewise, post-decrement or decrement happens after the statement is evaluated. So you would compute your entire line and then increment or decrement the variable. There's some relational operators, so how you do comparisons between values. All of the relational operators produce a logic value as the result. In C, logic is represented with either 0 or 1 as a value, or rather 0 as false and a non-zero value is true. So the relational operators should all produce a 0 and 1, but know that if you have a non-zero value, by default, C considers that as a true value. So you can check that variables contain the same value with equality, or don't contain the same value with non-equality. You can see if the raw value that they hold is larger or smaller than the other, and likewise larger or equal to, or smaller or equal to. So anywhere that uses a truth value will likely have some kind of comparison involved, and that's what the relational operators are used for. We also can, of course, support logical operations. So C supports a subset of the kind of logical operations that we talked about before. So with these logical operators, we're basically treating a variable as a single bit value, so a 0 or 1, even if they're not storing a 0 or 1. So again, we're treating them as if they're a logic value in the eyes of C. So if they're 0 or non-zero. And of course, we support our old friends and, or, and not. And with these 3 logical operators, you can represent other operators, as we discussed. There's also a new logical operator called the ternary. So the ternary is this pair of question mark and semicolon. And the way this statement is evaluated is basically if the thing that is here, so if A, either a variable or a compound statement, if A is true, then this whole statement evaluates to B. So the value that is yielded by this statement is just B, whatever B contains. And likewise, if A, the variable or compound statement, evaluates to false, then this whole thing evaluates to just C, or the variable value that's contained in C. Sometimes you'll see this. It's not super common. And the last kind of operator that C supports is the bitwise operators that we talked about. So bitwise AND, which compares all of the individual bits in A and B. So for index 0, the 0th bit in A and 0th bit in B, if those are both true, then the resulting integral type will also have a 1 in that position. Likewise, there's bitwise OR and bitwise XOR. The notation for bitwise XOR is a little confusing. This is not doing a mathematical power operation. The reason this character is used is because there was a limited number of characters to pick from. With the, like at the time C was developed, ASCII didn't have the ability to represent like the character that we would usually associate with XOR. So that like circular symbol with a plus inside of it that we had used previously, that didn't exist in the character set because it was so specific. So they had to make do and this is what ended up being used to represent XOR operations. So bitwise not inverts all of the bits in A, and you should take note that a bitwise not is not a logical not. So a logical not produces either a 0 or a 1, depending on whether or not the statement or variable passed to it is non-zero. The bitwise not, again, does that bitwise inversion of all positions in the value, or in the variable. And of course, we also support left and right shifts. So these shifts also do the sign extension. So if you're doing a rightward shift on an unsigned integer, it'll shift in zeros at the most significant bits. But if you're using signed integers, and that signed integer happens to be a negative value, so there will be a 1, since we're using the 2's complement representation in binary, there will be a 1 in the most significant bit, and that 1 is sign extended with C's right shifts. There are a few more operators, but they deserve a more lengthy discussion, so we'll get to those. C also does allow you to express arithmetic and bitwise operations as part of an assignment statement. So for instance, here we're declaring variables A and B as type integer and initializing A to 0 and B to 1. These two statements are equivalent. So A plus B, and then assigning that value to A, or A plus equals B. Those are equivalent statements. So this is like compound assignment operator is a thing, and generally it's supported for all of the arithmetic operators. So all of these guys, whoops. Addition through modulus. Increment doesn't really make sense in that context. So these operators and the bitwise operators. I've never seen a shift equals, but I think it exists. A different kind of modifier, so something that you can write before this data type declaration, like out here, is const, and that just dictates that this variable, after it's been initialized, should never change. And when you're building your program, C will give you an error if you attempt to modify a const qualified variable. All of these operators do have an order of operations, and it's basically identical to what you'd expect given the order of operations in traditional arithmetic. You can bypass that by use of parentheses. So here, the multiplication operator has a higher precedence in the order of operations than the addition. So the multiplication happens first when you're working with these variables. So the value that ends up stored in V1 is 7. But if we add parentheses, we give that everything in the parentheses a higher precedence than everything else. You can nest parentheses, and it's just the highest nested set of parentheses, that body of code that has the highest order of precedence. So here we surround the body A plus B in parentheses, and so that's evaluated first. So we get 3, and then we do the multiplication. So this value stored in V2 is 9 instead of 7. So when working with data types, it is common to realize, oh, my data actually needs to be interpreted as a different format for this specific application, even if the variable is denoted as a specific type. So in order to change how the type is interpreted, but without changing the underlying value, we use something called a typecast. Typecasts behave differently for different kinds of types. So if you're going from an integral type to an integral type, all you have to worry about is the size. If the variables hold the same number of bytes, so same number of bits, the cast just takes the raw bit implementation. So like if you're going from a signed integer 32-bit width to an unsigned integer 32-bit width, all it does is copy the bits directly when you do a cast. if you're going from a smaller variable to a larger variable, so a uint 8, casting that to a uint 32, all it does is a sign extension. So this is what's known as promoting that data. And then you just do the assignment. But if you're assigning a larger value into a smaller variable, the larger variable has to be truncated. So all of the leading number of bits up until the width of the smaller variable, those are cut off. That doesn't keep into account sign extension. So if you're going from like an int 32 to a uint 8, I would consider that a dangerous operation unless you know what you're doing, because you're cutting off a large number of bits, and you may end up losing the sign of your signed integer by doing so. For incompatible types, so if you're going from an integer to a floating point variable, for instance, the floating point variable is just assigned the whole number value. So a float is capable of representing whole numbers, except the floats have some precision to them. So the float is given the value of the whole number that's closest to the integer value that you're trying to represent. So if the float can't natively represent the whole number, that's a problem. And so you get a value that's closest to that whole number. But if you're assigning a float value to an int, the float has to be floored to the nearest whole number. In the case where you're assigning a negative number float to a negative number integer, it gives you the closest value to 0. So instead of taking the floor, it takes the ceiling. But it gives you the closest value to 0. You can either have an implicit cast, so you don't invoke any new syntax, and C will automatically do the interpretation for you depending on the data type of the variable that you're storing into. So for this example, I have two 8-bit integers. One is unsigned, so A is unsigned, and B is signed. If B has a value of -1, then in binary via 2's complement representation, that'll be all ones. So each bit will be set. When I do the assignment of B into A, there's an implicit cast that happens here. So if A must be an unsigned integer, then B is cast to an unsigned integer. Luckily, they both share the same size, but that means that A as an unsigned integer, if in binary it has all set bits, then it now holds the value 255. So it's pretty important to know what kind of data you're working with, and generally you want to have all your data typecast be explicit. So when your typecast is explicit, it means you have specific syntax that you as the programmer have inserted to ensure that a specific variable is interpreted as a certain data type, even if it's not declared as such in memory. So I'm going to compare two operations that we do here. We're going to declare two integers, A and B. When you do this division up here, you're dividing A by B, but as an integer. So the result is going to be some integer value that's been truncated to the closest whole number because of the fact that you're using two integers as the operands here. So the variable C that's storing the floating point value just picks up the whole number that's a result of this operation. So when you actually perform this computation, C is truncated to 0. So if you're dividing 1 by 2, you'll get 0.5. And so the closest whole number value to 0 is just 0. But we can perform an explicit typecast here. So if you have variable A, we're going to cast it to a float. And that means that the machine is now going to interpret this as a floating point variable A, which means that this division is now a floating point division. So B is also implicitly cast to a floating point value now. And the result of this operation is a floating point value. So 1 over 2, 0.5, and now D stores 0.5. So I would recommend using explicit casts anytime that you're converting between different data types, because implicit casts can be tricky and aren't visible to the naked eye. So if you didn't know that A and B up here were two different signed integer types, then this statement wouldn't let you know as a programmer that there's a cast going on. But you want to know as a programmer that there's a cast going on. So what you would do in this case is if the cast is intentional, just make it explicit. You can cast away a const qualifier, but that isn't recommended to do. There are certain scenarios where that's necessary, but for the most part, you don't want to do that. There is one last way of kind of influencing how a variable is interpreted in terms of data type, and that's by how you feed it its initial value. So, instead of all variables in this expression, we could instead have like a raw value that we express here. So whenever we talk about a raw value that can either be assignable or operated on, we're talking about a value literal in C. So these expressions 1 and 2, or -1 up here, are all literals. So we are assigning a literal value to B. Naturally, there are a bunch of different kinds of literals. For integers, you can represent decimal literals, and that's what we've been working with so far. But you can also represent octal and hexadecimal literals, and those are just integers that are in base 8 or base 16. So there are different conventions to represent them. So octal literals have to start with a 0. So notice that none of these values have a leading 0, other than when you're just expressing 0, which is identical across integer and octal representations. And then hexadecimal you represent with this 0x. When we're talking about the hexadecimal variable, I would say this is hex 1a. The reason you need to use like A through F is because if hex is base 16, our decimal representation for numbers only extends up to 9. So 0 through 9 digits. So we just needed to borrow some new characters to represent values that are greater than 10, basically. So you have 0 through 9, and then A through F represents the values 10 through 15 in base 16. So for this number, that would be A, or 10, is in the 16 to the 0 power place, and 1 is in the 16 to the 1 power place. So you have 16 plus 10, or a decimal 26. Hexadecimal values, or hexadecimal literals, are pretty commonly used, especially when you want to represent raw bit values. So like hex 0f would represent 8-bit value that the first 4 bits are all 0 and the last 4 bits are all 1. And I'll let you think about why that's the case. You can also, for integer literals, specify like a hint as to the size of the variable that you're going to use to store it, and also the signedness of the variable that you're going to use to store it. So if I had like a hexadecimal value, like hex 1a, I could specify that it's unsigned with this u suffix, and that it should be stored in a long integer with this l suffix. For floating point, it gets a little trickier. By default, if you just represent like a decimal value, so 2.1, that's actually a double. You could also represent a double as exponential notation. So this would be 4.0 to the -2 power. So this e is actually how you represent that mathematical power as a literal. Let's see. So if you're taking 4.0 to the -2 power, that's just the square root. So that's decimal 2. It's also possible to represent long doubles, as we discussed with the primitive data types, by appending suffix L. Or if you want just a single precision floating point value as a literal, you would append suffix F. So those are mutually exclusive. So a long double has fundamentally a different size than a float. So you're not ever going to see like 2.1 FL. That doesn't exist. 2.1 F, that's a float. 2.1 L, that's a long double. Character literals are, so if a character represents a printable, like English text character, then character literals store those values as human readable text. And the way you store a character is just by enclosing it in single quotes. So this would store whatever ASCII value is associated with letter A. You can also use character literals to represent things that, like special characters. So when working with like a raw text file, if you wanted to represent a tab, we could store that as a character via this like special escape sequenced T. So escape T, so this backslash is an escape character. And when we use backslash T, that indicates that this T doesn't represent a letter T, it actually represents a special case. So in this case, these backslash T represents a horizontal tab. And if you go look at that ASCII table, which I think I have linked up in the character section, ASCII does define what these special characters actually are. It doesn't define what the C representation for the escape sequence is, so that you'll have to look up separately. Another really common escape sequence you see is backslash N, which represents a new line. So if I wanted to represent like this paragraph in C, then this line break here, after the word suffix, I would have to insert a backslash N in C to represent that there's a line that's created here. So a string is a sequence of characters, and you can represent a string literal in double quotes. So anything that's valid as a character is valid in a string. So you'll see individual characters that are represented in sequence, but you can also represent escape characters. So note that this is actually one character. So it's this literal contains the sequence of characters that would be used to represent this text. So hello world, followed by a new line, followed by a null character. So all strings are null terminated. So there's a hidden character containing value 0 at the end of this string. That becomes relevant later. So with our example of typecast up here, you could also do the same thing by using a careful application of a literal. So if A is an integer value holding value 2, we can, instead of having a variable here that needs to be typecast to a float, we could represent a float directly. So because this is a floating point value, this becomes a floating point division. Again, we'll get 1 divided by 2, so B will still result in 0.5. But if this had been an integer literal that we express, this would have been an integer division, because A is also integer type. So this is just ways in which we can represent data in C. So variable definitions followed by their data type and interpreting that data type. But now we actually want to do things with that data. So we have a set of operators that we can use, but maybe we want to have a decision-making capability or do things repeatedly.
Hey, Michael.
Sorry, yeah, I missed your comment, Alex.
Yeah, I was just going to point out on the exponential, the 4.0 e negative 2, that's not decimal 2, right? That should be 0.04. 4 times 10 to the negative 2.
To tell you the truth, I've never used this notation before. I could be wrong about this. When I looked it up, it was to this power, but I could be wrong for sure.
Gotcha. Okay, I'm pretty sure that it goes time. It's like you're specifying times 10 to the whatever power.
Let me look that
Typically.
up real quick. Yeah, I think you're probably right. I'll correct that when I release the notes.
Okay, cool. Thanks.
Okay, so we have the ability to declare that there are memory addresses that are associated with specific types of data, and we can operate on them, and we can interpret the types of that information. So now we want to do some decision making. So in C, any kind of decision making is done by a conditional statement, so something that's evaluated on a logical basis, so either a 0 or non-zero value. And we did briefly talk about one of the operators that can do this, so the ternary. So the ternary does some conditional evaluation of A. So if A is a compound statement, the resulting value of that statement is what's evaluated. And based on the result of that conditional statement, if it's 0 or non-zero, you can take action in the form of returning value B or C. But that's kind of limited because it means that these positions B and C, which can either be variables or compound statements enclosed in parentheses, it means that we can't have complex operations happen here. So in order to represent bodies of statements, we use the new syntax if or if else. So these statements just declare that there is a body of code that will execute if the condition within the parentheses here evaluates to true. And the way we represent the body of code is by enclosing it in a set of braces. So this if-else statement, which follows this if. So an else statement must follow an if statement. And it basically just says if the evaluated conditional is not true, then do this. So when you pair an else with an if, it just means that after evaluating this condition and finding it to be false, we then need to evaluate this condition. And then if that's true, you can do all of the operations contained in the body. So you can chain these indefinitely. You can have the first if statement followed by a series of else if statements, and you can end it there if you wanted to. So, or you can end it with one else statement that doesn't have a conditional expression to evaluate. And that just means if whatever came first evaluates to false, this condition handles whatever opposite exists. So if this, let's say this else if also fails this conditional evaluation, this else would automatically run. So the body of an else statement is only run when all the conditionals that precede it don't return true. Likewise, you can have a standalone if statement. So you don't have to use else if or else. So the statements that are evaluated as conditionals can also be compound statements. So recall this is the logical and this is logical not. So if A is true and not B is true, in this case they're both false, so this doesn't get run. But this compound statement is taken as a single conditional statement. So this evaluates to a logical value of 0 or 1 in the eyes of this if. You can also, instead of doing a bunch of if and then else if, you can also use a different kind of structure called a switch case. So if the conditional statements in if are evaluated as logic, so a 0 or 1, the statements evaluated for the switch are actually evaluated as integers. The specific type doesn't matter as long as it's integral. And what a switch case does is basically takes the value encoded by its parameter and maps it to one of several cases that are represented. So in this case, our value to evaluate is 2. So we'll go to case 2 and run any code that exists in case 2. So the body of case 2 is just everything after this semicolon. One tricky part here is this, this term break. Break is used to exit a case statement. So that wherever you see break defines the exit of the body. Yeah, sorry. So Nicole asks an interesting question. Integral types is any just kind of integer. Likewise, floating point types is any kind of float or double. So yes, integral types are all just integers. So this is an integral type that's evaluated here. Yeah, getting back to it. So case 1 here doesn't have a break statement. So that means its body extends until the next break. So if I have some switch statement that evaluates to 1, it'll go to case 1 and recognize that its body is actually everything below here. So case 1 actually evaluates also to case 2. That's just a tricky thing that you can do using the switch case syntax. You don't have to do that, but there are certain cases where it's useful. So if I were to write this as an if-else tree, I would say like if our state is 1 or 2, then evaluate this body. And that would be the equivalent statement in an if-else like tree. It's also really important in switch statements to include a default statement. So if the evaluated value, so let's say this was 5 instead. 5 doesn't actually have a case that's represented under this switch body. So it would go to the default case instead. Default handles anything that isn't represented as a discrete case. You'll also notice that the switch contains its body in these braces, just like if. So in summary, the ternary, the question mark, is useful for cases where you just need to evaluate a value. But if else can be used to represent bodies of statements that the ternary can't. And if you need a giant set of conditional statements to evaluate, so for instance, evaluating a state machine, the switch case structure is really useful for that. So that's decision making. But if we want to repeat actions, we need to use something called a loop. So the simplest kind of loop is a while loop, and the while loop evaluates a conditional as well as a logical value. So if this counter value is non-zero, this while loop continues. So here we'll have this while loop evaluate starting at counter value 5. 5 is non-zero. We execute some code. We decrement the counter. And so now at the next loop, the condition is evaluated again. So the counter value is now 4. And we repeat this process until the counter value is non-zero. Or sorry, until the counter value is 0. So as soon as counter is 0, this conditional evaluation returns false. And so our program would move to below the while statement. So it would avoid this body and continue to the next instruction. Do while is very similar, except it just evaluates the body before evaluating the conditional statement. So this do while would evaluate the statement C equals B and then look to the condition. So if we're looking at value A, that's 0. So if they logic false, so the do does not loop. Hope that's clear. The last kind of loop that C exposes is called a for loop. And for loops are very common in programming. The basic syntax in C is you declare a loop that has some initial statement that's evaluated before the loop starts. The conditional statement that's evaluated at every loop before the body is evaluated. and then some statement that occurs after the loop has evaluated, but before the next loop starts. So in this example, we define some integer, and then we declare our for loop. So the initial value that we're setting here is we're declaring this temporary variable I with initial value of 0. And this happens before the loop starts. And then the loop starts. So the for loop evaluates its conditional statement. So while I is less than 5, then this loop will continue. So condition is evaluated. Now we go into the body, a plus equals I. So we're adding 0 on this first iteration. And then the after statement occurs. So after the loop body has evaluated, we go here. So here we're incrementing this variable I. So I is now 1. So the complete loop cycle has completed. And so now we go into the next loop cycle where we evaluate the conditional statement again. So now that I is 1, we do this comparison. I is still less than 5. We go into the body, evaluate it, and continue to the after statement. So this will continue until the conditional value is false. So as soon as we increment I to the value of 5, this for loop evaluates the condition statement again. 5 is not less than 5. So the for loop concludes. And if you follow through the logic, we're adding the value of I every time, and I is incrementing every time up to 5. So A ends up with a value of 10 for this example. So again, it's the initial statement occurs before the loop starts. The condition is evaluated at the start of every loop, then the body, and then the after statement until the condition is no longer true. There are 2 other statements that are relevant for use in loops. So we already talked about break in the case of switch case trees, but break can also be used in loops. And when a break statement is found in some kind of loop, it immediately exits the loop, regardless of what the conditional is currently evaluating to. So for instance, in this while loop, if I inserted break after this statement, so down here, then the while loop would exit immediately. So even if the counter value still contains a logically true value, we immediately exit the loop and continue to the next instruction afterwards. Likewise, there's a statement called continue. And if I did the same thing, if I put in this statement continue just before this statement counter decrement, so if I put it like here, then continue would cause this loop to jump to the next iteration of the loop. So it would skip the remaining body in the loop and then go immediately to the conditional evaluation. And that also holds true for loops. So sometimes you'll see those when you want to do control flow that doesn't necessarily need the entire loop to execute. So now that we have both operators, decision-making capabilities through if or switch case, and the ability to repeatedly take some action, it would also be helpful to be able to group these statements together like subroutines. So in C, we don't have the kind of generic subroutine that assembly implements. We instead have a function. And it's similar to the concept of a mathematical function that is mapping some input to some output, except you can also change other variables that are visible within the function. So yeah, so C functions can also change the state of variables that are neither inputs or outputs, depending on if that variable is visible within the function. So functions are also declared and then defined. So when you declare a function, you're just describing that it exists so that it has some output type and some inputs and its name. And when you define it, you're giving it a body. So the group of statements that will be associated with the function. So the declaration typically has the syntax where you describe the return type. So this is a data type that the function will produce when it runs. You have the function name, and then in parentheses, you have a comma-separated list of variable definitions, or sorry, variable declarations. So you'll have like a variable type followed by the variable name with a comma. The parameters that are passed here can either be the full variable definition or declaration, or they can just be a type. And when it's just a type, you access those parameters positionally. That's kind of an advanced use that I'm not going to talk about. For the most part, you want C to just have the parameters defined by their data type and a name, just like any other variable. And a parameter is just anything that's considered an input to the function, as seen within the function. The return is the value and associated type that the function produces when it operates. Note that in C, it's not possible to have multiple returns. Some languages do support that, but not C. So as an example, the
Michael,
function...
you got a question about the while.
Yes. Yeah, back up in the loops. Yeah, so if counter, because this, whatever is in these parentheses is evaluated as a logical statement. So because counter is a non-zero value, it's is conditionally evaluated to true. If counter was 0, then it would be evaluated to false. And that's just C's convention for handling logic values, so true or false. Right. So function definitions are almost identical to their declarations. So like I mentioned, you have the return type of this function. This function is called add integers. It returns an integer and takes 2 integers as parameters, a and b. So when we define the function, we're actually giving it a body. So a set of statements that's to operate when the function is used or invoked. So in this case, we're storing a temporary variable c that's defined within the function. And it's just the sum of the 2 parameters. And we're returning that value. So when we say return here, we take the value that's declared. Sorry, we take the statement or function or variable, we evaluate it to a value, and then we return that value. So just like assembly, when we jumped into a subroutine, we would call that calling the subroutine. We can also call functions. So when you call a function, the actual data that you're passing in to those parameters, those are called arguments. So the values that get received by the function are the arguments. The parameters are these variable names that are used within the function to do computations. So that's a subtle distinction. So for this example, we're still using add integers. So we have a declaration, and we're assuming it's defined elsewhere. We'll declare some variables, d and e, with certain values. And then the syntax for getting the return value from this function looks like so. So we're passing variables d and e in. So those the values of d and e are going to be passed in by value as arguments to add integers. Add integers then performs the computation in its formal definition and returns a value. So this evaluates to the return value of add integers. In this case, D and E are 1 and 5, so F should contain 6. Because this function call, so you're providing the function name and then some arguments in parentheses that constitutes the call. Because that evaluates to a value, we can also use it in compound statements. So we can treat it as if it's just an integer value because that's its return type. So here we're adding F to itself. Sorry, we're adding F and this result, and then we're restoring the value in F. Likewise, because this evaluates to an integer. It can also be used as the argument to another function. So here we're using the results of this first add integers call as the first argument to another add integers call. So whenever you have a function that can return a value, you can treat it in code as if it's just a value. Worthy of note is that all arguments to functions in C are passed by value, which means a copy of the value stored in either the variable or the literal passed to a function is made, and that's what the function is working with. So when I say like add integers D and E, add integers can't actually change these variables D and E because a copy of the value is what's actually given to the function. So as another example, if we define this function internal counter, which just increments this parameter A and gives us the value of that result. When I define this variable B and pass it in as an argument to internal counter, I'll get the result, which is B plus 1. So C will store 2. But notice that I'm doing an increment here that's operating on the parameter. So this value A is changing, but this value A is local to the function. So the parameter is a variable that's only visible within the function. So A is incremented, yes, and we return A. But the variable that's passed here, since it's passed by value, B is unchanged when this function runs. That distinction is really subtle. Does it make sense to everybody?
Yeah, that makes sense.
All right. If you have questions on that, please put them in the chat. And then, of course, functions can optionally return no value or take no parameters. And the way you specify that is with the handy void data type. So if we define a function that has return type void, it means that it doesn't pass a value back. You can still have return statements within a function that returns void or no data. You just can't declare that you're returning some value because according to your function definition, you're not. The reason this is useful is because you can conditionally return from a function. So like we could have a statement, if A, then return. Otherwise, we would do things. So if A is true, then we return early from the function. But in this case, it just means we're exiting the function as soon as we hit this return statement. So this expression is not valid because this function, which should be no return, doesn't actually return a value. So B has no value to store. So this would throw an error when we attempt to build our code. A lack of parameters can also be denoted by the void data type. But more commonly, you'll see it as just a set of empty parentheses. Both of these are valid to represent a function that has no parameters. You can nest functions. So this is one kind of nesting of a function where we take the output and provide it as input to another function. But there's a special case of nesting that's known as recursion, where a function will call itself internally. So I mentioned when we were talking about assembly, you could have subroutines that nest. So the special case of recursion is just when your subroutine jumps to itself, and in C that would be a function calling itself internally in its body. So if this internal counter had another call to internal counter somewhere in the body where we passed a variable in and used the result for something, that would be an example of recursion. So in C, all of the function calls occur on a stack, So we talked about in assembly subroutines having stack frames. So the like a saved state of the machine registers and potentially some other variables or memory addresses that are pushed onto the stack when we enter a new subroutine. Something very similar happens in C when we call a function. So we save the state of the machine prior to entering the function call. So that's saved on the call stack in this case. With recursive cases, it's capable to run out of stack space if your recursion goes too deep. So if you have too many calls that call themselves. And the condition where you run out of stack space to represent further function calls, so the computer can no longer save more state to enter a new function, that's called a stack overflow. So that's, I don't know if you guys are familiar, there's a website called Stack Overflow that's helpful for programmers. That's where the name comes from. As I noted up here, you can also define new variables within a function. But you can't define a function within another function. So all the functions have to be defined kind of at the global level. Any variables that are defined within a function are also stuck onto the call stack as part of the stack frame. It also means that those variables kind of disappear from visibility as soon as you exit the function call. So by default, you can't or shouldn't reference variables that are defined within functions after you exit the function. So here's an example of recursion. You just have a function call with the same name as the function that's being evaluated. This computes the Fibonacci sequence. These two conditional statements dictate what the end case for this recursion actually is. So if the parameter that you're providing, if its value is 0, then the Fibonacci sequence of that index is just 0. If you're providing 1, the Fibonacci sequence returns 1. Otherwise, the Fibonacci number at the index follows this recursive pattern. And I can let you guys follow the logic through because we're running out of time. Another really important concept in C is this idea of scope. So I've been mentioning repeatedly data visibility. So where a variable can be seen. And where a variable can be seen is defined exclusively by its scope. So scope is by default global. So like this function is defined at a global level, i.e. it should be visible everywhere. Everywhere that can see its declaration. Likewise, any variables that are not defined within functions are also considered global. So this would be considered a global variable. Global variables and functions and other data types that are defined outside of functions are visible basically everywhere that they have a definition. So in the case where like you're splitting your C program across multiple files, you just have to have a declaration that your variable or function exists in each of those files to be able to use that global variable or global function across all of those files. A variable that's defined within a function is said to have local scope. And local scope just means it's only visible within that function or block definition. Let's see. You technically can reuse variable names if you have one that's defined at global scope and one that's defined at local scope, because the local scope will only look at the local variable name. It's not recommended to do this, and I would specifically recommend against repeating variable names because it gets confusing. Just know that it is possible. And the last kind of scope is the special case of a local variable for the parameters that are passed into a function. So technically, this integer n isn't actually defined within the function, but it is visible within the function. So n is treated like a local variable, even though it doesn't have a full declaration within this Fibonacci function. So you can also have a local variable defined within an if statement. So here we have a deeply nested local scope context. So we have global variables. We have a global function definition. We have a local variable due to param being a parameter to this function. We have a local variable that's declared within the function. You can access the global variables from within any scope because they're visible everywhere. And here we're adding it to this local variable and storing the result in the global variable. You can also, like I mentioned, have local variables defined within like conditional statement blocks. There are other kinds of blocks. There are even blocks that have no operation. So you can define just an arbitrary block where this variable, local example 2, is not visible outside this block. It's not really common to see this, but it's sometimes useful when you're when you have a variable name that you really want to reuse for some reason. So note that as soon as you start nesting scope, the local variable or set of local variables that are defined in the deepest nesting position are not visible anywhere else. Does that make sense to everybody? Because that's pretty important.
Yeah.
Okay.
Yeah, makes sense.
Okay. So this section gets a little complicated. It's still useful, even if we have this like myriad ways of representing information in memory and operating on them, and doing so by variable name, as opposed to assembly, which only works with addresses. Sometimes it's still really useful to work with addresses, even in C. So C just makes it easier to work with addresses by providing two operators, the address of operator and the dereference operator. The address of operator, so this ampersand, just gets the address of a variable. And we can store that in a special kind of data type known as a pointer. So in this example, we're taking the address of A, which is a variable that has some memory location. And so we're getting the memory location of that variable. And we're storing it in this pointer to data type int. And we're calling that pointer ptra. So this is the syntax for declaring the pointer type. A pointer does need to know what kind of data it points to, so that when you dereference the pointer using this syntax, so dereferencing is getting the value that's stored at that pointer. When you do the dereference, you need to know the data type so that you can store it appropriately. So i.e., so there isn't a type collision. And that's just so that you can have a statement just like this. So if A was a float and pointer A was a pointer to float, C would need to know that this evaluates to a float type so that it can do the implicit cast. So the syntax of declaring pointer is just the data type followed by the pointer special character followed by the name of the pointer variable. So this is just like any other variable. It is a value that is stored in a memory location. And in this case, the value is a memory address. And the memory location is just wherever this variable happens to be stored in memory. So this is like any other variable. The fact that it stores an address is just the special case that we're going to encounter. So the only reason why we need this special syntax is so that we know that it's a memory address that's stored in this variable. Like in theory, you could cast this memory address to integer type, or however large of a type can store a memory address on your machine. And you can do so, it's valid. You'll just get the memory address as a binary bit field. But the use of storing it in a dedicated pointer type is that we know that this value is a variable. So it increases clarity of the program. You can also dereference a pointer and then assign it a value. So we can treat it when it's used on the left-hand side of an assignment or within some kind of compound operation. When you dereference that pointer, you're now getting access to the memory location that's represented. So here, when we dereference pointer A and assign it value of 10, we're really storing this value 10 in A. Does that make sense to everybody?
Yes.
Cool. Okay, so when we talked about our computer representation, recall that we talked about the memory addresses all having a fixed width. So the width of the address defines like how much memory your machine has. In C, since pointers are variables and they store addresses, all of the pointers are the same size. So this pointer is not the size of an integer. This pointer is the size of the memory address of your machine. Likewise, if we had like float pointer, that would have the same size as this integer pointer when we're talking about the pointer itself. So the pointer is a variable and its data is just the memory address. So the size of the variable, like its bit width, is just the bit width of the memory address on your machine when we're talking about pointers. There is a special value for pointers called the null pointer, and it's just represented in C with uppercase NULL. And that represents the special value of address 0. And typically, your machine won't allow you to access memory address 0, so C uses it as a special value to represent a pointer that doesn't currently point to any valid memory. So by default, if we had a declaration of pointer A without this initialization, so say we had a semicolon right here, that would get initialized to null. So that pointer would not be pointing to anything. We would then have to assign an address to it later to be able to dereference it appropriately. So if you dereference a null pointer, that's actually an error. And you can't determine that at time of build. So this error would happen after you're already executing your code. So it's like one of the worst possible bugs that you can encounter. So it's very important to know when your pointer contains the value of null, because it could cause your machine to crash if you dereference it. It's also possible to nest pointers. So you could have a pointer to a pointer, but this shouldn't come as a surprise because a pointer is fundamentally a variable. So here we have a pointer to integer, which is in this case pointing to variable A. And here we have a pointer to a pointer. So the syntax looks like we have a pointer to integer. And that's how you could interpret it. So in this case here we have a pointer to pointer, and we are pointing to this variable ptra. We can also dereference it by just dereferencing this first pointer. So when this dereference occurs, we now evaluate to pointer A, and then we can dereference pointer A. So this, again, just evaluates to the value held by A. So yeah, you can nest pointers basically infinitely if you wanted to, as long as you have enough space to represent a valid variable at the end of that pointer chain. So remember when we were talking about functions, how I was talking about everything being passed by value? If you pass a pointer, you can actually access the variable that's passed in. So the if we pass a pointer as a parameter, that address is passed by value, but then we can dereference the address and access the underlying memory used for that variable. So in effect, passing a pointer allows us to modify the input parameters to a function. Whereas if we didn't pass a pointer, if we passed the variable directly as an argument, we just get a copy of its value that's not changeable. So here, foo is this function that increments the parameter that's given to it. When we call foo, it is not able to change its input. Bar, however, is a function that takes a pointer to some variable as a parameter. We dereference it, and I use parentheses here to denote that the dereference happens first, just to avoid any kind of confusion with this operator. So we dereference the parameter. So we're now pointing to some memory address that's evaluated here, and we're incrementing whatever is at that memory address. So here, when we pass the address of A as a pointer into bar, when we call bar, it'll dereference that pointer. So bar will access whatever memory location A is stored at directly, and then increment it. So bar is actually able to change the value stored at A using this mechanism. And this is really common in both embedded systems, systems programming, and application development. Because a lot of times you need to be able to produce more than one value as a result of the function executing. So if you had like an input list of parameters, let's say one variable that's passed by value, or one plain variable that's passed in, and then a set of pointers. And that plain variable needs to determine the output values that you want from your function. Instead of using a return, you could pass a bunch of pointers into your function, do some operation, and then dereference each of those pointers to store the results. And that would be kind of the workaround for there only being one return type for a function in C. As I keep mentioning, pointers are variables, so you can do arithmetic with them. You can't really do anything else other than arithmetic with pointers, just because it wouldn't make sense to do so using a memory address. But the arithmetic operations that are supported on pointers are just increment, decrement, addition with some integral value, and subtraction with some integral value. You can also use relational operators. So you can assign values to pointers, as we've seen. You can use the special compound assignment. You can use equality and inequality. I didn't mention it here, but you can also use the relational, so less than or less than equal, greater than equal, to compare memory addresses directly. So one specific use of pointer arithmetic is if you have contiguous memory addresses. So for this example, when we declare variables A0, A1, and A2, these are given contiguous spots in memory. So A0 is stored, and then A1 is stored, and so on. If we do pointer arithmetic, it's possible to access A2 without using its name. The way we would do that is we would take the first memory address that we're accessing. So the first memory address in this contiguous segment, we store its address in a pointer. And then we can do some arithmetic on the pointer. So here we're just adding 2 to the pointer and storing that address natively. Okay, Alex, do you want to cut it off in like 5 minutes then? Okay. There isn't too much left. Yeah, so here we are doing some integer arithmetic using a pointer. Something that's really important to know, though, is that most computers store, like when we talk about an address with most computers, it's actually referring to an 8-bit segment in memory. and that's just by convention. So 8-bit values or bytes are kind of the fundamental data width in a computer, at least with the perspective of C. So when we do pointer arithmetic, we actually take into account the data type that's used. So here, because this is an integer type, when we do this pointer arithmetic, we're actually adding 2 times the size of the integer value. So if this had been a character instead, the address would increment by 1, so pointing to the next byte, because the character is of size byte. But because we're using an integer, and I'm assuming this is a 32-bit machine, we're actually adding 4 to the address when we do this increment, because we're actually adding 8 here, because the integer is size 4 bytes or 32 bits, and we're adding 2. We're incrementing twice. So we're finding the next, whenever we increment by 1 for a pointer to integer, we're finding the next location in memory where an integer could occur. So for this case, if we added 1 to the pointer, if the pointer first pointed to this variable, we would find the next valid place that an integer could occur in contiguous memory, which is the same place where A1 is defined. So here, when we're adding 2, we increment the pointer twice. So PA now points to A2. But it's still worth noting that the address itself increments by, whenever we increment once, the address actually increments by the size in bytes of the data that's being pointed to. And you'll see why when we talk about arrays. So just like when we were working with regular variables, we can dereference the pointer now. So if we point to A2, we can dereference that and store the value 10, where this variable points to. So A2 will receive a value of 10 from this assignment. Likewise, you can use any of the other arithmetic operators that I talk about up here when we do pointer arithmetic. The last thing I think we'll actually be able to get to today is the concept of an array. So if we have a lot of contiguous memory segments, let's say 100 contiguous memory elements, it would be a serious pain to have to type out all of those variables. So C provides a shorthand that's called an array. So in C, an array is just something that we're considering a collection of memory. So it's a number of addresses that are in sequence, and an array stores a specific data type. So when we declare an array, we have the data type that's stored in memory, and this is so that we know how to increment the certain number of addresses to find the next valid variable. We have the name of the array, and then we have this, this pair of square brackets within denoting the size of the array. So when we do this declaration, it means that we're storing a space of 10 integers contiguous in memory somewhere, and we're referring to that by this name, array0. The array name is, under the hood, actually a pointer to the first element in the array. We can also initialize this array using an initializer list. So it's just a block containing several literals separated by commas. So this array is defined with length 10. However, we are initializing the first 4 positions with the values in this initializer list. So if we actually looked into memory, what we would see is at this first position, so the 0 index of the array, we store the first value, and so on, up until position 4, which was not part of this initializer list. So it remains uninitialized. It's whatever state memory was in prior to us declaring this variable. If you omit the number here, so the number of elements, so if you have like a set of empty brackets, the array size will just match however many numbers or elements are in this initializer list. So for this example, we have 4 elements in the initializer list, so the array length is 4, and the valid indices, when we're talking about this array, are indices 0 through 3. We can index into the array using those indices. So array index 0 holds value 5. So this statement evaluates to value 5, and we can store that in variable A. Likewise, index 3 points to this segment of memory within the array. So this evaluates to 6, and B stores 6. If we attempt to access an index that's not technically in the valid array length, then it produces an error. So here, in both cases, so if we're accessing index 4, that would be beyond the memory space that this array allocates. And if we access negative, or try to access index -1, that's also beyond the space that this array allocates. So those 2 positions, if we try to access those indices, it would cause an error. Usually we can catch this when we build, but not always. So always know the size of the array you're working with. You can also represent multi-dimensional arrays. Really, this just designates a format for how you're indexing into the array. But fundamentally, the array is just a contiguous segment of memory. So you have some number of bytes that's allocated for this, like this one variable that contains, by syntax, other variables. So you can index into a multi-dimensional array just by using multiple brackets. So the first bracket indicates the row, and the second bracket indicates the column for a 2-dimensional array. But really, this is just what's called syntactic sugar on top of pointers. So like I said, the array name is really just a pointer to the first value in the array. And whenever we're doing indexing here, we're really doing pointer arithmetic based on the first value in that array. So an equivalent statement to this would be like, well, let's take a simpler example. Array at 0 would just be the pointer that array holds plus 0. And this would be the pointer that array, the variable name, holds plus 3. And this is fundamentally why C indexes by 0. So 0 is the first element of the array because it's the array pointer plus 0. And that's by definition. The last thing I think we have time to talk about is the concept of a string. So I talked about string literals being just sequences of characters. We can work with a sequence of characters as an array of character type. So a set of contiguous memory locations of size character that is indexed into. And we have to remember that any string has the last position containing the null character, so a value of 0. So yeah, next time we'll finish up C, and I will get into microcontroller theory, and then we can talk about the project. So I think Alex had some ending remarks.
Well, yeah. Yeah, I wanted to just kind of open this up, I guess, for some questions. This is, I mean, we went from like pretty basic C intro kind of stuff into like pretty complex topics here. So, oh, and I guess Nicole has a question about why the array, if you want to answer that.
That's a feature that a lot of other languages provide. So accessing an array by index -1 in a language like Python, it'll wrap around to the end of the array, but in C, that's not a valid operation. So in Python, you're not doing pointer math directly, which is why this could be a valid statement for Python. But in C, because you're using pointer math under the hood, because this evaluates to taking the address of the first element and then subtracting 1, you've now got a pointer to a memory address that's defined before your array. So C doesn't allow you to do that because you could access invalid memory.
Cool. So yeah, I guess I just wanted to kind of make sure that some things are outlined and everything. So that int is like 8 bits, at least we're assuming that for right now. So it's 8 or 4?
Yeah, so all of the integer types, any data type is at minimum 8 bits. That you can kind of rely on. I don't think I know of any computers that have a fundamental unit that is smaller than 8 bits in memory.
Okay. And then, so something like long though, or float, those could be longer, like 64 bits, something like that.
In theory, there is no limit to the size of a variable other than what your machine can provide natively. So if your machine has like 64-bit compatible instructions, then it can do 64-bit integer arithmetic. And so you can have a 64-bit type in C.
Gotcha. And so even though the bit sizes are different for each of those, the pointer for both of those, for an int, a long, a float, all of those sorts of things, is the same fixed size of 8 bits?
Yes. So we're assuming that each memory address points to an 8-bit area in memory. So if we have a multi-byte variable, let's say an int, if we're working on a 32-bit machine and our ints are 32 bits by default, your pointer will actually point to either the most significant bit or least significant bit within that integer. And then C will know that because it's an int data type, you'll also have 3 bytes that are trailing that pointer. So what you actually point to, the memory address that's stored in the pointer, is actually the location of one of the 4 bytes in the integer.
Gotcha.
Usually
and
it's
so that's
like the most significant one.
And so that's why when you increment the pointer by 1, you basically move up by, let's say, 4. Or and does that change, by the way, for if you go from int to now you're using pointers for like a long or a float? If you increment by 1, it's not going to just increment by 4, would it?
So if
does it increment by the size of the
the pointer
type?
The address held by the pointer, if you're adding 1 to the pointer, the address held by the pointer would increment by the number of bytes in the data type represented by what you're pointing to. So for a double, that would be 64 bits or 8 bytes. So every time you increment a pointer to double, it would internally, that address that it's storing would be added. You would add 8.
Cool.
So the pointer arithmetic is the address is incremented by the number of bytes in the data type you're pointing to. That's probably the most concise way of stating it.
Okay. And then let's see, what's Nicole's other question?
So Nicole, you're talking about this this example. Yeah. So when you do an assignment into a pointer, the address that the pointer holds is assigned a new value. So yeah, you lose having a pointer to A0 at that case. We could save a pointer to A0, so we could copy PA. We could assign PA to a new pointer before we do this pointer arithmetic, and that is frequently used as a technique. The size of the int would not change because, so when you declare the pointer, the pointer's data type is pointer to some other data type. And so this pointer can only ever hold pointers to int, for instance. there is a way of working around like not knowing what data you're pointing to, and that's by using a void pointer. I didn't actually end up talking about that, but I should later. A void pointer can, you'll assume that it points to the smallest memory kind representable on your machine. So I think void pointers all point to like 8-bit unsigned integer by default. Don't quote me on that. But the use of a void pointer is that you can cast it to a pointer of another type. So if you cast, if you say like uint8t pointer pb, and you assign it typecast. Actually, let me type this in chat. So if you had something like so if we declare uint8t, so if we defined a pointer to uint8t called pb, we could assign pa into it if we did a cast. So pb is.
Yeah, I don't think I can see where you're writing.
Oh, shoot. I sent that to Alex by default. My bad. Let me just.
Do you want to just do it on the screen? Yeah.
Yeah. Okay. So working from this example, so we have int pointer PA that holds address of A, A0. If we then defined, let's say, uint8t pointer PB, and we assigned it a typecast pointer. So here we are casting the address held in PA to now point to a uint8 type. Then we would get a pointer to the first memory address in A0. So we would get that first 8-bit value. If we then did PB equals to, let's just increment instead. If we then incremented PB, because the data that it's pointing to is an 8-bit value, the address would also increment by 1 byte. So the address increments by 1. So that's the only case in which the pointer arithmetic can change in value, and that's if you intentionally cast it to a different, to a pointer to a different data type. Whereas PA++ by 4. Does that make sense?
Wait, I was looking at the third line in the website, and I'm not sure why that what that comment means.
Which website?
Like the one that you're reading from during the lecture.
Yeah.
The third line has
So
that
line
comment.
right here?
Yeah, I wasn't sure what that comment meant.
Yeah. Okay. So the size of the integer is the number of bytes that it contains, because bytes are the fundamental unit that C looks at as addressable memory. Because we're adding 2 to the pointer, the actual address that's stored in the pointer is incremented by 2 times the size of the thing that's pointed to. So here we have a pointer to integer. Integers are 4 bytes for a 32-bit machine. So the actual address is incremented by 8 because we have integer size of 4 bytes. If you increment by 1, that's the next valid integer is found at a memory address that is 4 greater than the last. And so when we're adding 2, we're really just adding 2 times the next valid address for an integer. So let's say our memory looks like this. So let's say we're storing an integer that has value 1. In memory, it would look something like this. So you would have all of the most significant bytes first for some machines. Byte ordering is machine dependent. I'm not going to get into that though. So you would have some number of bytes, and then the last byte, so the least significant byte, holds your bit of 1. So in memory, when we address, we were talking about 8-bit memory locations. So I'm representing those in hexadecimal right now. But the pointer to an integer type is fundamentally an address. So it would store address 0 for this example. The pointer to an unsigned integer 8 bits is also an address. So when you're talking about a pointer to 32-bit integer type, your pointer stores this value of 0. But when you're doing the integer arithmetic, you want to know, like, if this series of memory addresses, so if these 4 bytes in memory represent the full integer, and C knows that your full integer contains the value of 1, then it needs all 4 of these addresses. When you're doing pointer arithmetic, you want to find the next valid integer. So it'll be the next 4 addresses. So when we do the pointer arithmetic, the actual address increments by 4 when you're talking about an integer.
Oh, I see what you mean. Wait,
So
so each bit has an address, or
each byte has an address by convention. So each 8 bits, each address points to a memory area that is 8 bits in length. So that's this hex value.
wait, so what's the size of that integer? Is that 4 bytes?
Yes. So right now, for this example, I'm assuming a 32-bit integer is represented on the machine.
Got it.
32 bits is 4 bytes. So hence, C would look at these 4 memory addresses as related because we're declaring int A0 in memory. So this would be A0, and the pointer would point to the first byte. So the whole like pointer arithmetic is really just C's way of messing with addresses. For this example, when I have pointer B, if I cast pointer A to hold a pointer to uint 8t, then really C would look at it as the same thing, a pointer that holds an address that is this address. However, when we work with it, so when we dereference it or when we increment, increment it or when we dereference it, it treats it as an 8-bit value, so a single byte. So when we do pointer arithmetic and increment PB, PB would now point here, the next valid 8 bits. There's this concept of alignment, which is like where it's valid to have integers allocated in memory. And usually integers have to be byte aligned, which means starting at 0, they have to be in the next valid memory address, assuming that your entire memory is filled up with integers. So like if we had an integer, it would have to be on a boundary that is a multiple of 4 because there are 4 bytes in length. An 8-bit integer doesn't have that kind of boundary restriction. A 64-bit integer would have to be like on a multiple of 8 with its address. There's a way of getting around that. I might talk about it later, but we're getting into kind of like advanced topics.
Next week, huh? Yeah. So, all right, cool. I think that's pretty much it. I'm gonna post the link for just in the chat here if everyone wants to go check this out.
Looks like Lucas has
Oh
one
man.
Thanks,
last
Alex.
I have one more question I put in the chat right there. It's kind of long, sorry.
All right, so there is that. I want to get this out just so that everyone kind of has access to this if anyone does need to run. This is just the form for the, what is it? The audio amplifier kit. So fill that out if you want to, get one of those. And it's just going to be first come, first serve. So we're posting it here, and then I'll post it into the Slack and in the email later, probably tomorrow or something like that. Anyway, sorry, yeah, Michael, if you want to.
Sorry. So Lucas asks, you shouldn't use global variables. Generally, that is true. Using global variables is a really easy way to add complexity to your program that it probably doesn't need. I mentioned it because the idea of global scope is so important, because functions can only be declared and used, declared at global scope. But global variables can exist. Though I would agree with the instructors that it's not a good idea to use them for storing data. So pointers and memory references seem like globals. So if pointers are variables, pointers can still be declared in local scope. So you can have a void function called foo, and it takes parameter a that's a pointer to an integer. You can then define int pointer b. So this is valid. So here, this pointer b is in local scope. So that is a local variable. So I'm not sure what you mean by seeming like globals.
Okay, I think I'm just trying to kind of figure out why my professor said like not to use globals and stuff. So I guess it's looking at that, it's probably less like I was thinking it's just because it's outside of the local scope and like you should do everything in the local scope, but maybe
my examples up here are definitely in global scope.
Oh yeah.
You're correct about that.
But maybe like why they're trying to say that is more because of just like not wanting to complicate things with a bunch of stuff at the global level and like run out of variable names and stuff like that, rather than like just the concept of accessing stuff that's not in the local scope. If you know what I mean.
Yeah. It gets cluttered if you use a lot of globals.
There are also some security reasons for it too. Yeah.
Yeah. So
like
for instance, if you're defining if you're defining some set of functionality, so you have a function and some globals that it operates on, you wouldn't want an external program to be able to reach into a global and modify it if your function isn't expecting that global to be modified by anything else than itself.
Okay.
So that's one use for scope, in that you can hide variables effectively from external programs.
Yeah, that's kind of the reasons I was taught, was just unless it needs to be global, make it local to make sure that nobody else accidentally modifies it or purposefully, maliciously modifies it.
Right. Yeah. So I guess that kind of leads to like the core of my question, which is why use like pointers and memory addresses and stuff when you could do it in variables?
Well, for starters, you can't modify a variable inside of a function unless it's visible within that function. So the whole idea of passing variables to a function is so that we don't have to use global variables at all. And that's in part due to security, yes, but also for code organization purposes. So without pointers, you can't actually access the data that you're passing to a function. You have to operate on the values that you're given and then return something. So if you want a function to manage accessing and setting a variable, usually you have to pass a pointer to it. There are also other cases like something I'm not really going to get into is dynamic memory allocation. So if you're working within an operating system environment, you're usually given the option to, instead of allocating things on the stack, so via like local variable declarations and the global data space, instead of using those areas, there's another area called a heap. But I don't really want to get into it, but when you do dynamic memory allocation, you're given a pointer to somewhere in that memory. So the real distinction is when I'm making a declaration of a variable like this, I know where it's going in memory in relation to everything else I've already declared. When I'm doing dynamic memory allocation, I don't know where it is. So the system has to give me a pointer to this allocated segment of memory that it's given me.
Okay.
So the answer is pointers are useful as programmatic constructs. If you don't want to use pointers, you can totally use global variables. But at that point, why not just use assembly?
Right. Okay, so it just kind of like lets you get a little bit lower down at a lower level, and makes it easier to kind of work there and points and stuff. You know?
Yeah, there are. I was going to get into this later. It's helpful in microcontrollers because you have like fixed memory addresses where things exist. And if you know those addresses ahead of time, you can create a pointer to them and access them through that pointer. Whereas if you just declare a variable as a global, you won't be able to access the resource that already exists at a specific location. And I'll talk about this in detail as soon as we get into microcontrollers.
Interesting. Yeah, that's I thought it must be something like that because it seems like it's getting a little bit more machine specific. So that's probably kind of why it's useful with microcontrollers, right?
Yeah. So like what I'm going to talk about is like memory mapped hardware devices. So like you have a memory address where the bits represent things to a memory or some kind of hardware device. And in order to access that hardware device, you have to be able to access that specific memory address. And that happens through pointers.
Okay, very cool. All right, I'll hang on and see where we're going with this. I'm excited.
Yeah, so next time I'm going to finish up C. I'm going to give you guys some live demos of like writing what actual C code would look like and how I would organize it. And then we're going to get into microcontroller specifics, so theory and then hopefully tools. This workshop may end up running over into a 7th day, depending on how long next time takes. I hope you guys don't have that Saturday blocked out because that's probably when I'll end up being able to talk about the project. But yeah, I'm looking forward to finishing C next time and getting into microcontroller theory specifically. Do you guys have anything else?
I think all good.
I don't think so. Thank you.
Cool. Thank you.
Apologies that this ran over. There's going to be a lot more content to talk about next time too. Notes will be up tonight, and so will the video.
Sweet. Thank you, Michael.
Awesome. Thank you, Michael.
Thank you.
Michael.
Thanks.
Thank you. Have a great
Thank
weekend.
Yeah, talk to you guys next time.
Thanks everyone for coming.